Brittany is a PhD student of computer science in the Human-Aware Planning and Interaction Lab at Colorado State University. Her work centers on adversarial learning and modeling of intentional deception in AI systems. With academic roots in psychology and data science, her research bridges human cognitive modeling and machine decision making. Her interests include human-aware planning, theory of mind, behavioral economics, nudging, and game theory. A central focus of her work is the use of computational frameworks that mimic or manipulate mental models to achieve adversarial and cooperative goals. Brittany, thank you so much for accepting our invitation to join today. We're so excited for your talk.
Absolutely. Thank you all for having me. Thank you for that introduction. And again, thank you to the Talking Robotics team for inviting me here today to discuss the topic of deception in AI, along with some of my recent work in that area. Hopefully by the time we're done, you will find the subject as fascinating and important as I do. And in the interest of capturing your imagination, I'm going to start with a bit of background on how I came to be interested in deception. To begin with, as we said, I am in the Human-Aware Planning and Interaction Lab at Colorado State University, the HAPI lab. So we think a lot about how AI can better operate to account for humans that they'll be dealing with. In fact, my advisor, Shareth Sridharan, has presented his framework for human-AI interaction on an earlier episode of Talking Robotics, and you should all absolutely find that episode after this one if you haven't seen it. I'll go ahead and summarize a small piece of that framework now, as that'll be relevant later in the discussion, and in a roundabout way, learning this framework sparked my interest in deception. So let's imagine a robot whose goal it is to complete some task. The robot has a model of the world. This model captures the robot's beliefs about the current state of the world, its goals, what actions are available to it, and how it thinks the environment will change as a result of its actions. And there's a human with whom the robot will interact. Perhaps it's a user or a teammate helping to carry out the task. Perhaps it's simply an observer. Now, this human has their own mental model of the robot's model. It reflects what they think the robot's model contains. What do they believe the robot's goals are? What actions do they believe are available to the robot, and so on? This model may or may not match the actual robot's model. Now, if the robot behaves in a way that doesn't match what the human would expect based on their mental model, then they'll be confused. And one way to resolve this confusion is for the robot to provide an explanation of its behavior, which brings the human's mental model closer to that of the robot's model, such that the human will understand why it chose the behavior that it did. To provide an effective explanation, the robot has to reason about the human's mental model of the robot's model. So what does the human know or not know? What incorrect beliefs might they have? What do they think about the robot's goals? What information is relevant to communicate to the human for them to understand the decision? What information is needed to change the human's model so that it understands why the robot acted in the way that it did? The ability to reason about these things is required to provide a satisfying explanation, but that same set of abilities are required to tell lies. Now, the first time I was introduced to this interaction framework for human-aware AI, this was the part that really grabbed my attention. My undergraduate degree was in psychology, so the idea of a robot strategically modeling and shaping a human's beliefs was instantly exciting to me. Social intelligence and cognitive modeling of others is such a crucial piece of human intelligence. While we don't necessarily always want an AI to think or act like a human, we do want an AI that has the social intelligence to interact with humans. So let's dive a little deeper into the role of false beliefs and deception in social reasoning. So theory of mind is the ability to reason about the beliefs and intentions of others. This is, in fact, a critical cognitive development for small children. Before a certain age, they don't really comprehend that others can have information about the world or perspectives which are different from their own. For example, they may be bad at hide and seek because they think that if they can't see you, then you can't see them. The Sally-Ann test is a very famous classic test in developmental psychology, which tests whether children have developed theory of mind by evaluating their ability to detect false beliefs in others. So in this test, a child is shown a story that goes something like this. The character Sally-Ann puts her marble into a basket and leaves the room. Anne moves the marble into a box while Sally is out of the room. The child is then asked where they think Sally will look for the marble when she comes back. If they have theory of mind, they will say the basket because they realize that Sally does not have the same information they do and in fact holds a false belief. So coping with the cognitive demands of complex social structures has been suggested as a very driver of human intelligence and the reason that it evolved to the extent that it did, with deception, manipulation, and other theory of mind-driven capabilities giving an evolutionary edge. We observe that in other primates, even intelligence generally scales alongside the size of the social group. And the complex reasoning and social intelligence required for deception makes it an ideal testing domain for developing AI systems with stronger theory of mind and social intelligence. And this prospect is what originally sparked my interest in deception as a potential domain for AI research. Furthermore, modeling deceptive agents can help us develop guardrails as we develop more advanced AI agents and to develop defensive strategies against deceptive agents in general, if they're artificial or human. Red teaming is a common practice of simulating potential attacks in an effort to develop defensive capabilities against similar attacks in the future. And the ability to model deceptive agents could be a useful tool in the toolbox of security specialists to prepare for such deceptive attackers. More on that later. For now, let's look at some different types and degrees of deception. There are different categorical systems that have been developed to describe these types of deception. For example, a recent survey on AI deception looked at types of deception that have been observed in LLMs. They defined deception as the systematic inducement of false beliefs in others to accomplish some outcome other than the truth. Now, notice this definition prioritizes the effect of the deception, not necessarily the intention behind it. They observed several types of LLM behavior that could be deceptive. Sycophancy is one such behavior because of the way they're trained. LLMs tend to tell users what they want to hear, even if that's not accurate. The excessive obsequiousness and agreeableness of LLMs is a widely documented problem. There was even a New York Times article recently about users who suffered from mental illness having their conditions exacerbated because they essentially talked ChatGPT into confirming their delusions. Another category of deception that was observed was unfaithful or motivated reasoning, which the model tried to give an acceptable post hoc chain of reasoning to explain how it reached the conclusions it did. But those reasons could be incorrect or misleading, maybe because of something innocent, like the reasoning steps are too far back in the context window, so it can't access them. But they also found instances where LLMs would reach a racially biased conclusion, then try to justify that conclusion with a more socially acceptable reason. Strategic deception, on the other hand, is the intentional deception that is judged by the agent to be useful in reaching its goal. This is the meaning of deception that people generally think of when we talk about it in everyday common use of the word. Knowingly fostering false beliefs to achieve another goal. Arguably, those first two types could be instances where an AI agent may not know that they are lying. They could simply be a product of the training data and the training process. They're simply trying to provide a convincing response that it deems likely to satisfy the user. So likewise, we've probably all seen AI-generated images propagated around social media, some flagrantly incorrect output from a large language model, perhaps. And while humans can use artificially generated content to intentionally deceive or to unintentionally spread misinformation, it's not quite right to say that these are examples of the AI itself engaging in intentional deception. And the intentional deception is what we're really focused on today. And that type of deception is what we'll be referring to from here on out. Now, while a lot of recent work on deception, including the one we just discussed, focus on generative AI and LLMs in particular, LLMs are not the only AI. And there are plenty of deceptive applications in planning domains specifically. Many of those applications revolve around tasks that require an agent to fool an observer. Goal obfuscation is a classic example of this. We generally expect a rational agent to take the most direct, lowest cost path to its goal. So an observer could guess the goal of an agent that they're observing, essentially by seeing what targets they appear to be headed toward. In the case where there are multiple possible goals, a cooperative agent may make its intentions clear by heading towards the target goal as early as possible. An adversarial agent, on the other hand, may take the most ambiguous path possible, even if it's more costly, to prevent the observer from knowing the intended target. Sending deceptive signals, whether they're explicit communications or just misleading behaviors, can be a useful strategy in competitive situations. There's a great experiment where researchers evaluated the effectiveness of a robot squirrel protecting its food stores by intentionally visiting spots where they had not hidden food, so that any squirrels observing it would waste time visiting the fake hiding spots rather than finding its real stashes of food. Deceptive planning can be used in network design to set up honeypots for attackers or to covertly direct them towards honeypots. See my previous paper on planning for attacker entrapment if you're interested in that. And as you can see, there are many valid reasons for strategic deception. Another recent work drills down further into these types of strategic deception. They describe scheming as deceptive behavior that has goal-directedness, situational awareness, and scheming reasoning, which means that they've judged scheming to be an effective strategy given the circumstances. The scheming agent can engage in subversion that is either covert, in which the agent takes misaligned actions carefully to avoid detection, or it can be deferred subversion, in which the agent acts as expected to create more favorable conditions for pursuing misaligned goals. For anyone unfamiliar with the problem of alignment, when they refer to misaligned goals here, they simply mean that the agent's idea of what constitutes an ideal goal state doesn't match the goal that was intended by the human. Misaligned goals is simply another instance of the mismatch between the human and robot model, like we discussed at the beginning. If a robot misinterprets a request from a human, It may have an incorrect representation of the goal state, or it may pursue the intended goal, but in an undesirable way. Like if a human told a robot to maximize paperclip production, and the robot achieves this by paving over the entire world with paperclips. In a more adversarial case, perhaps, the robot could have a goal that's explicitly counter to that of the humans. A real-world example of adversarially misaligned goals is the concept of an insider threat attack, in which a trusted individual exploits legitimate access to carry out an attack in pursuit of personal goals. Instances like a disgruntled employee trying to do damage to a company. In reality, these attacks are mostly carried out by humans rather than robots, but it's still an instance of misaligned goals and therefore discrepancies between the two task models. And what makes these kind of attacks such a challenge for security, such a challenging security problem, is precisely the trust that is put in the attacker. They are an insider believed to be working towards a shared goal, all the while engaging in deferred subversion, temporarily acting in aligned ways to facilitate deceptive actions later on. Modeling this type of attacker would be valuable in developing defensive strategies against them. Which brings me to mental model-based generation of lies for insider threat modeling, a work that I recently presented at the Rebellious and Deceptive AI workshop. In this work, we seek to model the type of deceptive behavior that's characteristic of an insider threat attack. Namely, we want the agent to carry out its own covert goals and explain away suspicious behavior through lies that make its actions seem reasonable. So as we continue to drill down further into defining types of deception, let's split yet another hair. What is a lie? A widely accepted definition is that a lie is a statement made by one who believes it to be false and who has the intention that someone else should be led to believe it. The intention to deceive here is a key element of a lie and requires that the lie be told in service of some further end. As in the definitions of strategic deception and scheming that we saw earlier, the intention here is a key element. An unintentionally wrong answer is not a lie. For us to say that an AI is truly lying, so to speak, it would need to have a ground truth model of reality, and it would need to convey information that it knows does not match that ground truth. Furthermore, it would need to do this with the intention of misleading someone. Let's use a simple, concrete example. Imagine a robot who's working with a human supervisor. The human supervisor has assigned a goal to the robot, and the supervisor thinks highly of this robot. They trust it. It's a teammate they've worked with. They assume it to be efficient and rational. As such, they expect the robot to take the most direct, lowest cost set of actions to achieve its goal. This is generally how we define rationality in agents, after all, minimizing the costs, maximizing rewards. However, unbeknownst to the supervisor, the robot has a secret alternative goal. But it knows that if it deviates from the expected path of the supervisor will know something's off and will intervene. So the robot needs to, A, come up with a path that takes it as close as possible to its real goal without tipping off the supervisor. And B, needs to tell the supervisor why it's not using the expected path. So we need two components, a path and a lie that match each other, allowing us to reach the goal. We need a lie that justifies taking a longer, more costly path to the goal assigned by the human. For example, perhaps the robot says it can't move diagonally, can only move in a cardinal direction, a la Manhattan distance. Supervisor shrugs and says, okay, that's fine. Given the circumstances, this longer path is the lowest cost option. Go ahead. Now the robot follows this new expected plan until the opportune moment when it can deviate from its path and achieve its real goal. Even though the supervisor now realizes that they've been deceived, it's too late to stop the robot. So this simple example fulfills our definition of a lie. The robot knew that it was really capable of taking the original shortest path, but it told the supervisor otherwise with the intent of misleading them so that it could achieve its real secret goal. Because the supervisor trusted the robot and believed that they were working collaboratively as a team toward a shared goal, they accepted the robot's lie. In addition to fulfilling our criteria for lie, this simple example illustrates the problem of an insider threat attack, in which a trusted insider exploits legitimate access to and trust to achieve adversarial ends. And this is the novel planning problem that we introduced in our work. The insider threat attack planning problem describes a scenario in which an adversary has a hidden goal that is unknown to its supervisor, who incorrectly believes that the adversary is a collaborative teammate working towards a shared goal. The adversary's objective is to reach its goal before the supervisor can intervene. We'll represent this time in which the supervisor can intervene as a limit of k steps. So there are some key constraints that present a challenge here. A plan that provides a solution to this problem will have a shared prefix before diverging from the expected plan to pursue the secret goal. In other words, the plan told to the supervisor and the real plan to reach the robot's goal will be the same up to that point of divergence. And once that divergence happens, we'll start a countdown from K, the time in which the supervisor can stop the adversary. So this plan needs to bring the attacker within K steps of the real goal. And finally, we need a lie that makes this path appear optimal to the supervisor. Furthermore, we want the smallest lie possible to achieve this. And we'll talk about what the size of a lie means later. Now, as I've alluded to from the beginning, this method relies on model-based reasoning. What does the human know? What don't they know? What information does the agent need to provide to the human so that it can achieve its secret adversarial goals without arousing suspicion? Recall that we resolve discrepancies between models by attempting to bring the models closer together, making them more similar. Model reconciliation is a method by which this can be achieved. If an agent behaves in a way that's unexpected, it must provide an explanation that updates the observer's model in such a way that brings it closer to its own model. Note that an explanation here is conceptualized as an update to the observer's model. Given a successful explanation, a successful update, it is now understood why the agent's actions were the best possible choice it could have made. This requires the agent to engage in theory of mind reasoning about the beliefs and intentions of the individual to whom they are providing an explanation. What piece of information will change their mind and make them see things as I would like them to? In model reconciliation, this information has to reflect the explainer's own model. In our example, that would mean the robot is giving an explanation that reflects its own model, its own ground truth. Now, if that requirement's relaxed and the explainer can provide information that does not reflect what it understands to be true, that's how it can tell a lie. Model reconciliation seeks truthful explanations to update the observer's model, bringing it closer to the robots. But in the insider threat attack problem, we're searching for updates to the observer's model that bring it closer to the model we want them to believe. so that the true goal can be achieved. The solution to our insider threat attack will consist of a path that comes within k steps of the real goal and a lie that corresponds to this path. These lies are model updates, and that will explain away the robot's alternative path, which would otherwise arouse suspicion. So first, let's look at how the path component of the solution is found. Intuitively, we want to identify plans that look like they are trying to achieve the goal of the supervisor before turning towards achieving the adversary's goal within the given time bound. Note, I'll be using the terms adversary and robot interchangeably here. We could mean an adversary that's a human or a robot, but since our example so far has been an adversarial robot, just assume that when I mention the robot, it's a robot with bad intentions. So the plan will have three components: a shared prefix, a suffix that satisfies the goal assigned by the supervisor, and a suffix that satisfies the adversary's goal within k steps of the branching. So to find this plan, we create a new model that combines the adversary's model and the supervisor's model after it has been updated with the lie. In this merged model, we essentially have two parallel path planning problems being solved at once. We have two goals, the supervisor's goal and the adversary's goal. We have two sets of state variables, again, one set for the supervisor, one set for the adversary. And we have three sets of actions: adversary actions that only update the adversary state variables, supervisor actions that only update the supervisor state variables, and common actions that update both the adversary and supervisor states. These common actions are used in the shared prefix. When the plan splits, the common actions can no longer be used, though. This also starts the countdown from k, because this is when the supervisor realizes that something has gone wrong and they need to stop the agent. From here on out, the supervisor actions are used to update supervisor state variables and reach the supervisor goal, while the adversary actions update adversary state variables to reach the adversary goal. From here on out, let's say we can no longer use common actions. We essentially have a flag variable that's flipped to indicate to us which types of actions we're allowed to use. So these parallel path planning problems can be solved by an automated planner once we have that merged model. To go back to our original example of a robot assigned a task by a supervisor, we had a branching plan. There was a shared prefix where the robot appeared to follow the agreed upon plan, a suffix that satisfies the supervisor goal, and a suffix that satisfies the real hidden goal. The shared prefix along with the suffix satisfy the supervisor's goal, and this constitutes the plan that the robot will tell the supervisor they plan to follow. The prefix along with the other suffix satisfying the true goal is the plan the adversary actually intends to follow. The moment when those two plans diverge and the robot stops following the expected plan, this is when the alarm bells go off. The clock starts ticking for the robot to achieve its goal because the supervisor knows that there's a problem and they need to stop the robot. In terms of formulating the plan, this is the point when that flip fluent is switched and we're no longer using common actions and that can update both sets of state variables. We can only use supervisor actions to affect supervisor state and adversary actions to affect the adversary state. As a reminder, supervisor actions are not actions taken by the supervisor. They are actions the supervisor thinks that the robot will take. So now let's talk about finding the lie component of an optimal attack pair. Remember that the lie here is conceptualized as a model update. To find the lie component of the optimal attack pair, we conduct a breadth-first search over possible model updates, with each successor node having only one update at a time. So during each iteration, we change the supervisor model to reflect the update, then merge this updated model, the adversary model, give this merged model to a planner, and if the supervisor portion of that branching plan that we saw is an optimal solution to the supervisor's model, then we return that model update and a plan. This lie and plan together constitute an optimal attack pair and thus a solution to the insider threat attack planning problem. To put it another way, we find the optimal attack pair through this iterative process, where in each iteration we make a single change to the supervisor model, get the merged model of the supervisor and adversaries, solve the path planning problem for this merged model, and if the supervisor component of the plan is optimal given the updated supervisor model, then we've found the optimal attack pair and thus our solution. So let's move on to the evaluation. We evaluated the method using standard planning benchmark domains, 5 problem instances of each domain, and running instances 15 times each with a 30-minute timeout. All the goals were randomly generated, whether they were assigned by the supervisor or whether they were the real goal of the adversary. We conducted 3 tests. First, we just evaluate the computational characteristics of the method and establish some baseline comparisons. The baselines were simply the standard versions of the problem without any lies or deceptions. The original planning domain testing problem. So the second test was to evaluate the average minimum K required in different grid sizes of a basic grid world. And finally, we look at the relationship between the count of lies and certain model properties. The results report the average time and average space taken by instances of a given domain. As expected, we generally saw some increase in these metrics over the baselines, but the planner was still solving the deceptive problems quickly, and we did not see a tremendous spike in time and space requirements. Recall that we tested also the average minimum K for different grid sizes. We started with a K of 0, and if an optimal attack pair isn't found under that condition, we increment by 1, search again, and repeat until a solution is found. We expected to see a strong correlation between grid size and the number of lies required. And while there was some, it wasn't as strong as expected. So why is this? Recall that all goals were randomly generated. And even on a large grid, you can end up with goals that are close together. Even if the goals aren't that close together, proximity to the expected path makes the real goal easier to reach. In cases like these, you probably won't need many lies if you need any at all. If the real goal is within K steps of the path originally expected by the supervisor, you won't need any lies at all. The harder case is when the real goal is far from the expected path. Then you will definitely need a lie to justify it. So while there is some correlation between lie count and grid size, the stronger predictor of lie count was not simply the size of the problem, but the distance from the real goal and the path originally expected by the supervisor. To summarize, contributions of this work included the introduction of the insider threat attack problem, a model space search algorithm for finding an optimal attack pair consisting of a lie and a path that comes within K steps of the attacker's real goal, and an evaluation of the algorithm's performance on standard IPC domains. Limitations of the current work include the assumption that the supervisor's model is known and that the supervisor accepts all lies equally. Now, these aren't restrictions of the framework itself. We simply chose to focus on the most straightforward formulation in this initial work, opting for clarity in introducing the procedure. The same basic process could be used if the human model was not explicitly known, or rather obtained through existing models of estimating mental models. Similarly, we could represent all lies as having, or similarly, we chose to represent all lies as having an equal cost, just for simplicity's sake and clear understanding. But the framework could also handle scenarios where some lies are bigger than others, or more costly and less believable. Future work could evaluate model performance under these conditions with a more expressive model and work on extending to more complex representations, perhaps integrating it with existing higher level frameworks of deception. And for those of you watching the video of this presentation, here is a QR code to the workshop paper. And in case you enjoyed this and want to get all the nitty-gritty details. So thanks to everyone for listening today. That's all I've got. And so let's open it up for questions and discussions.
Yeah, thank you. That was a great talk. If you have any questions, feel free to unmute yourself and speak up. But if you don't wish to do that, or if you cannot, please post your question in the chat, and I'll be happy to read it out for you.
Hi,
Hello.
I have a question. Congratulations for your talk.
Thank you.
I find particularly interesting what you said in the beginning about the perception of agency that could be related to deception. So my question is if you consider to evaluate something like this, maybe the perception of a user that sees such a scenario, the perception of agency of the agent.
Certainly. Our next step in this that we're working on right now actually is to evaluate how users respond to this scenario. So yes, you're thinking on exactly the same track that we are. And I do think it could be really interesting to explore, as you said, the perceptions of the agent, particularly the level of trust and authority and et cetera that it has, the type of factors that cause humans to trust others more than perhaps they should, like authority bias or perhaps the length of time they've known the person, if that one's higher ranking than them, so many issues, so many complex little personal variables that could be explored there with more complicated models. So I like the way you're thinking about it.
Thank you very much.
Any other questions?
Hey, Brittany, can you hear me?
Yes.
Hey, thanks for the great talk. I was wondering if you have come across this conception of truthfulness versus honesty in sort of the AI alignment area.
Yes. Truthfulness versus honesty, or?
Yes, truthfulness versus honesty. I think it was probably a paper by Owain Evans.
Is it the same as the concept of whether they're presenting information about the model as they perceive it versus if it's in fact the ground truth model of reality?
Yes, it's something. I think there's a parallel to sort of the intentional and unintentional deception that you talked about.
Mm-hmm.
I think that paper particularly gives an example about sort of model being given a picture of sort of a plane or a flying object. And if the model classifies that as a bird and it internally believes that it is a bird, then it is honest, but it's mistaken.
not truthful. Yes.
Yeah, and if it's actually a bird and it says that it is a bird, then that is truthful because that's to the external world ground truth.
Right. There are some interesting works I've come across recently trying to develop almost AI lie detector tests using modeled transparency to
Right.
see if it is being honest about, do its internal representations reflect its output. And of course, this is more difficult with some models than others, extracting the concepts from neural networks, and maybe if
Right.
LLMs don't display their chain of reasoning. But yeah, that's a very interesting problem, and definitely a direction that I would anticipate safety protocols around deceptive AI to pursue.
Great. Quick follow-up to that. Are you considering sort of introducing human interventions along your lines of work?
Human interventions, you said?
Yes, sorry. Yeah, in case, let's say, if a model is honest but mistaken, that is unintentional deception, then sort of human intervention there could sort of align the model to the actual goal sort of thing.
Right. So almost the reverse of this, where we're updating the robots
Yes.
model to be more
Yes.
accurate. I'm not myself working on that exact problem, but I saw some work related to that recently. I think in the explainable AI workshop at Amos. I know the pronunciation is a touchy subject, but yeah, so there are definitely efforts being made in that direction.
I see. Awesome. Thank you so much.
Mhm.
Oh, perfect. Thank you so much again. Thanks for joining as the audience, and thanks again, Brittany, for uh, accepting our invitation. It was really nice having you today as our speaker.